To determine the feeder size, consider the total load on the feeder, which is the sum of the loads of the individual rooftop units. The minimum circuit amps of each rooftop unit is 91 amps, which is sized for 100% of the heater load plus 125% of the largest motor. Since this includes the largest motor, consider this as the continuous load. The National Electrical Code article that addresses this topic is Article 440.33 Non-continuous loads. Loads that operate for less than 3 hours per day and have a demand factor of 125%. Continuous loads operate for more than 3 hours per day and have a demand factor of 100%. Since the electric heat in the rooftop units can be considered a continuous load, use the demand factor of 100%. Therefore, the total load on the feeder is total load equals 10 rooftop units times 91 minimum circuit amps times 1 demand factor equals 910 amps. The next standard size overcurrent protective device, or OCT, over the total load is the appropriate feeder size. In this case, the feeder should be rated for 100 amps, which is the same as the overcurrent protective devices for the individual rooftop units. Based on the given information, the feeder size to the panel feeding the 10 rooftop units should be 100 amps to handle the continuous load of the electric heaters. When dealing with electrical loads and feeder sizing, it's crucial to understand the concepts of continuous and non-continuous loads as defined by the National Electrical Code, or NEC. This understanding directly impacts the ampacity requirements for conductors and the selection of appropriate overcurrent protection. A continuous load is defined as a load where the maximum current is expected to continue for 3 hours or more. This definition stems from the potential for heat buildup in conductors and equipment when subjected to prolonged high current draw. The NEC mandates that for continuous loads, the overcurrent protection device, or OCT, be rated at not less than 125% of the continuous load. This 125% factor effectively derates the conductor's ampacity to account for the prolonged heating effect. Non-continuous loads, on the other hand, are those where the maximum current is not expected to continue for 3 hours or more. For these loads, the NEC generally allows the OCT to be sized at 100% of the load, assuming the conductor ampacity is sufficient. In the context of rooftop units with electric heaters, determining whether the heater load is continuous or non-continuous is paramount. If the heaters are expected to operate for extended periods, exceeding the 3-hour threshold, they must be treated as continuous loads. This necessitates applying the 125% factor when calculating the required feeder ampacity. To accurately determine feeder size, firstly calculate the total continuous load. This involves summing all continuous loads connected to the feeder. Remember to apply the 125% factor to each individual continuous load before summing them. Secondly, calculate the total non-continuous load, which is the sum of all non-continuous loads connected to the feeder. Thirdly, determine the total load, which is the sum of the total continuous load and the total non-continuous load. Fourthly, select the conductor size based on the total load. The conductor ampacity must be equal to or greater than the total load. Refer to NEC Table 310.15 to determine the appropriate conductor size based on its ampacity rating and insulation type. Fifthly, select the overcurrent protection device, or OCT. The OCT must be sized to protect the conductor from overcurrents. The NEC generally allows the OCT to be sized at the next standard size above the conductor ampacity, provided that the conductor ampacity is not less than the total load. In the specific scenario of multiple rooftop units with electric heaters, several factors must be considered. Firstly, diversity or demand factors. The NEC permits the application of demand factors in situations where it is unlikely that all loads will operate at their maximum simultaneously. Check NEC Article 220.42 for receptacle loads to see if demand factors could apply. If the rooftop units are controlled by a building management system that staggers their operation, a demand factor may be applicable, reducing the overall feeder size requirements. Secondly, motor loads. Rooftop units typically include motors for fans and compressors. The NEC provides specific rules for sizing conductors and overcurrent protection for motor circuits, outlined in NEC Article 430. These rules often require oversizing conductors and overcurrent devices to accommodate the motors and rush current during startup. Thirdly, voltage drop. Long feeder runs can result in significant voltage drop, which can negatively impact the performance of the connected equipment. The NEC recommends limiting voltage drop to 3% for feeders and 5% overall for feeders and branch circuits combined. To mitigate voltage drop, it may be necessary to increase the conductor size beyond the minimum ampacity requirements. In addition to the NEC requirements, local codes and regulations may impose additional requirements for feeder sizing. It is essential to consult with the local authority having jurisdiction, or ORJ, to ensure compliance with all applicable codes and standards. Proper feeder sizing is critical for ensuring the safe and reliable operation of electrical systems. Undersized feeders can overheat, leading to insulation degradation, conductor failure, and potentially fires. Oversized feeders, while safer, can result in increased material costs and may not be economically justifiable. A thorough understanding of the NEC requirements, coupled with careful consideration of the specific application, is essential for determining the optimal feeder size. When sizing feeders for multiple rooftop units, first, determine the minimum circuit ampacity, or MCA, for each rooftop unit, or RTU. The MCA is the minimum current carrying capacity required for the branch circuit that supplies the RTU. It is typically specified on the RTU nameplate and is calculated by the manufacturer based on the unit's various loads, including compressors, fans, and heaters. Second, determine the continuous and non-continuous loads for each RTU. Identify which loads are expected to operate for 3 hours or more continuously. Typically, the electric heaters in RTU are considered continuous loads, especially in climates where heating is required for extended periods. Third, apply the 125% factor to the continuous loads. Multiply the continuous load portion of the MCA by 1.25 as required by the NEC for continuous loads. Fourth, sum the continuous and non-continuous loads for each RTU. Add the result from step 3 to the non-continuous load portion of the MCA to obtain the total adjusted load for each RTU. Fifth, determine the total load for all RTU. Multiply the adjusted load per RTU by the number of RTU connected to the feeder. This provides the total current that the feeder must be capable of carrying. Sixth, apply any applicable demand factors. Depending on the specific application and the likelihood of all RTU operating at their maximum load simultaneously, a demand factor may be applied to reduce the total calculated load. Consult NEC Article 220 for guidance on demand factors. Seventh, select the appropriate conductor size. Based on the total calculated load, including any demand factors, select a conductor size that has an ampacity rating equal to or greater than the load. Refer to NEC Table 310.15 for conductor ampacity ratings considering the conductor's insulation type and installation conditions. 8th, select the appropriate overcurrent protection device, or OCPT. Choose an OCPT, such as a circuit breaker or fuses, that has a rating equal to or greater than the conductor ampacity but not less than the total calculated load. The OCPT protects the conductor from overloads and short circuits. 9th, consider voltage drop. Calculate the voltage drop for the feeder run to ensure that it does not exceed the maximum allowable voltage drop specified by the NEC, typically 3% for feeders. If the voltage drop is excessive, increase the conductor size to reduce the resistance and voltage drop. 10th, verify compliance with local codes and regulations. Consult with the local authority having jurisdiction, or ORJ, to ensure that the feeder sizing complies with all applicable local codes and regulations, which may have additional requirements or restrictions. Here's an example calculation. Assume you have 10 RTU, each with an MCA of 91 amps, where 70 amps is the continuous load, electric heater, and 21 amps is the non-continuous load, motor. Step 1. The MCA is 91 amps. Step 2. The continuous load is 70 amps and the non-continuous load is 21 amps. Step 3. multiply the continuous load by 1.2570 amps times 1.25 equals 87.5 amps. Step 4. Add the adjusted continuous load to the non-continuous load. 87.5 amps plus 21 amps equals 108.5 amps. Step 5. Multiply the adjusted load per RTU by the number of RTU. 108.5 amps times 10 RTU equals 1085 amps. Step 6. Apply a demand factor if applicable, assuming no demand factor for this example. Step 7. Select a conductor size with an ampacity of at least 1085 amps. This would likely require multiple conductors in parallel or a very large conductor size, depending on the insulation type and installation conditions. Step 8. Select an overcurrent protection device, or OCPT, with a rating of at least 1085 amps, or the next standard size up. Step 9. Calculate voltage drop and increase conductor size if necessary to meet voltage drop requirements. Step 10. Verify compliance with local codes and regulations. Remember that this is a simplified example, and the actual feeder sizing may require additional considerations, such as motor starting currents, ambient temperature correction factors, and conduit fill limitations. Always consult the NEC and local codes for specific requirements and guidance. Determining whether the electric heat in the rooftop units can be considered a continuous load necessitates careful evaluation of the operational characteristics of the heating system. Factors such as climate, building occupancy, and control strategies all play a role in determining the duration of heater operation. In climates with long, cold winters, the electric heaters may operate continuously for extended periods to maintain comfortable indoor temperatures. Conversely, in milder climates or during shoulder seasons, the heaters may cycle on and off more frequently, resulting in shorter periods of continuous operation. The occupancy of the building also influences the heater's duty cycle. Buildings with 24/7 occupancy, such as hospitals or data centers, typically require continuous heating to maintain consistent environmental conditions. Buildings with intermittent occupancy, such as schools or office buildings, may experience shorter heating cycles during unoccupied periods. Control strategies, such as thermostats and building automation systems, regulate the operation of the electric heaters based on temperature set points and occupancy schedules. Sophisticated control systems can optimize heater operation to minimize energy consumption while maintaining desired comfort levels. Data logging and monitoring can provide valuable insights into the actual operating patterns of the electric heaters. By tracking the duration and frequency of heater operation, engineers can accurately determine whether the heaters qualify as continuous loads. In situations where the heater's duty cycle is uncertain, it is prudent to assume that they are continuous loads and apply the 125% factor when sizing the feeder. This conservative approach ensures that the feeder has sufficient ampacity to handle the prolonged heating demand without overheating or causing nuisance tripping of overcurrent devices. The NEC provides guidance on applying demand factors to reduce the calculated load for feeders supplying multiple loads. Demand factors are based on the principle that not all loads will operate at their maximum simultaneously. The applicability of demand factors depends on the type of loads being served and the diversity of their operating cycles. For feeders supplying multiple rooftop units, the NEC permits the application of demand factors under certain conditions. NEC Article 220.12 allows a demand factor of 75% for the nameplate ratings of all electric space heating equipment if the connected load is 4 or more. This demand factor recognizes that it is unlikely that all rooftop units will operate at their maximum heating capacity simultaneously. The use of demand factors requires careful consideration of the specific application and the potential for load diversity. If the rooftop units are serving different zones or areas with varying heating requirements, a demand factor may be appropriate. However, if the rooftop units are serving a single zone or area with uniform heating requirements, a demand factor may not be justified. To accurately determine the appropriate demand factor, engineers should analyze historical load data, conduct load studies, and consult with building owners and operators to understand the building's occupancy patterns and heating requirements. The NEC provides tables and guidelines for applying demand factors to various types of loads. However, it is essential to exercise engineering judgment and consider the specific characteristics of the installation when determining the appropriate demand factor. In some cases, it may be necessary to perform a detailed load analysis to justify the use of a demand factor. When applying demand factors, it is crucial to ensure that the feeder has sufficient ampacity to handle the maximum expected load, even if the demand factor reduces the calculated load. The feeder must be sized to prevent overheating, voltage drop, and nuisance tripping of overcurrent devices. The overcurrent protection device must also be sized to protect the feeder conductors from overloads and short circuits. The NEC provides specific requirements for sizing overcurrent protection devices based on the conductor ampacity and the type of load being served. It is essential to comply with these requirements to ensure the safety and reliability of the electrical system. In addition to demand factors, other factors can influence the feeder size for multiple rooftop units. These factors include motor starting currents, ambient temperature correction factors, and conduit fill limitations. Motor starting currents can be significantly higher than the motor's running current, especially for large motors used in rooftop unit compressors. The NEC requires that conductors and overcurrent devices be sized to accommodate the motor's starting current without causing nuisance tripping. Ambient temperature correction factors must be applied to conductor ampacity ratings when the conductors are installed in environments with high ambient temperatures. The ampacity of a conductor decreases as its temperature increases. The NEC provides tables for adjusting conductor ampacity based on ambient temperature. Conduit fill limitations restrict the number and size of conductors that can be installed in a conduit. Overfilling a conduit can lead to overheating and insulation damage. The NEC specifies the maximum allowable conduit fill based on the conduit size and the type of conductors being used. To accurately determine the feeder size for multiple rooftop units, engineers must consider all of these factors and comply with the requirements of the NEC and local codes. It is essential to consult with qualified electrical contractors and engineers to ensure that the electrical system is designed and installed safely and correctly. In the context of feeder sizing for multiple rooftop units, the overcurrent protection device, or OCT, plays a crucial role in safeguarding the electrical system from overloads and short circuits. The OCT is typically a circuit breaker or a set of fuses that are designed to interrupt the flow of current when it exceeds a predetermined level. The selection of the appropriate OCT rating is critical for ensuring the safety and reliability of the electrical system. The OCT must be sized to protect the feeder conductors from overheating and potential damage caused by excessive current flow. The NEC provides specific requirements for sizing OCTs based on the conductor ampacity and the type of load being served. In general, the OCT rating should not exceed the conductor ampacity. However, there are exceptions to this rule, particularly for motor circuits and certain types of equipment. For motor circuits, the NEC allows the OCT rating to be increased to accommodate the motor's starting current, which can be significantly higher than its running current. The OCT must be capable of withstanding the motor's starting current without tripping, while still providing protection against overloads and short circuits. For certain types of equipment, such as air conditioners and heat pumps, the NEC allows the OCT rating to be sized based on the equipment's nameplate rating. The equipment's nameplate will specify the maximum OCT rating that is permitted for the equipment. When selecting an OCT for a feeder supplying multiple rooftop units, it is essential to consider the characteristics of the load and the potential for overloads and short circuits. The OCT must be capable of interrupting the fault current quickly and effectively to prevent damage to the equipment and the electrical system. The OCT should also be selected based on its interrupting rating, which is the maximum fault current that the OCT can safely interrupt. The interrupting rating must be greater than the available fault current at the OCT location. The available fault current is the maximum current that would flow in the event of a short circuit at that location. The available fault current can be calculated using engineering software or by consulting with the local utility company. In addition to the OCT rating and interrupting rating, other factors to consider when selecting an OCT include its type, voltage rating, and environmental conditions. The OCT type can be a circuit breaker or a fuse. Circuit breakers are resettable and can be reused after tripping, while fuses must be replaced after they blow. The voltage rating of the OP must be equal to or greater than the voltage of the circuit being protected. The OP must also be suitable for the environmental conditions in which it will be installed, such as temperature, humidity, and corrosive atmospheres. Proper selection and installation of OPs are essential for ensuring the safety and reliability of electrical systems. It is important to consult with qualified electrical contractors and engineers to ensure that the OPs are selected and installed correctly. In the context of voltage drop calculations for feeders supplying multiple rooftop units, voltage drop refers to the reduction in voltage that occurs along the length of the feeder conductors due to the impedance of the conductors. Excessive voltage drop can negatively impact the performance of the connected equipment, causing reduced efficiency, overheating, and premature failure. The NEC recommends limiting voltage drop to 3% for feeders and 5% overall for feeders and branch circuits combined. This means that the voltage at the end of the feeder should not be more than 3% lower than the voltage at the source. To calculate voltage drop, several factors must be considered, including the conductor length, conductor size, conductor material, current, and power factor. The conductor length is the distance from the source to the load. The conductor size is the cross-sectional area of the conductor. The conductor material is typically copper or aluminum. The current is the amount of current flowing through the conductor. The power factor is the ratio of real power to apparent power. The voltage drop can be calculated using the following formula: voltage drop equals current times impedance. The impedance is a measure of the conductor's resistance to the flow of alternating current. The impedance depends on the conductor's length, size, material, and frequency. To mitigate voltage drop, several strategies can be employed, including increasing the conductor size, shortening the conductor length, using conductors with lower impedance, and improving the power factor. Increasing the conductor size reduces the conductor's resistance and impedance, thereby reducing voltage drop. Shortening the conductor length reduces the overall impedance of the circuit, thereby reducing voltage drop. Using conductors with lower impedance, such as copper instead of aluminum, can also reduce voltage drop. Improving the power factor reduces the amount of reactive current flowing through the conductor, thereby reducing voltage drop. Power factor correction can be achieved by installing capacitors at the load. In addition to these strategies, voltage drop can also be mitigated by using a voltage regulator. A voltage regulator is a device that maintains a constant output voltage regardless of variations in the input voltage or load current. Voltage regulators can be installed at the source or at the load to compensate for voltage drop. When calculating voltage drop for feeders supplying multiple rooftop units, it is essential to consider the diversity of the load. If the rooftop units are serving different zones or areas with varying heating and cooling requirements, the load may be more diverse than if the rooftop units are serving a single zone or area with uniform requirements. The diversity of the load can affect the voltage drop calculation. It is also important to consider the starting current of the motors in the rooftop units. The starting current can be significantly higher than the running current, which can cause a temporary increase in voltage drop. The voltage drop during motor starting must be considered when sizing the feeder. Proper voltage drop calculations are essential for ensuring the safe and reliable operation of electrical systems. It is important to consult with qualified electrical contractors and engineers to ensure that the voltage drop is within acceptable limits.